Well, my role here is to bring to you the excitement of fundamental research on these topics, and even more so the excitement of joining our research, fundamental, rigorous, long-standing research with the visionary entrepreneurship. And I have to acknowledge Mario and the family, you are visionary entrepreneur. Uh, Let me start with the provocation. Okay. We have listened, we have heard of the complexity of the future energy system, but let me still speak a bit on the complexity. This is a scheme which is probably the most representative frame of what a future energy system will look like. A multiplicity of energy sources, a multiplicity of energy final uses, and in between an incredibly interconnected network where we will find more and more commodities, more and more carriers to play together in the attempt to provide the optimization of the energy system. And today, optimization of energy system is not only cost optimization, but it is optimization from the standpoint of emissions. Let me spend one word. We are all struggling about carbon dioxide. Carbon dioxide is not the only concern. Among the general concerns, we will face more and more troubles in access to sustainable access to material resources. We have already mentioned the problem of critical raw materials and the way critical raw materials may impact technologies that only 10 years ago looked very, very promising. And this is the reason why in this complex framework we have put a special emphasis on that block to the left up part, which is power to heat. Power to heat belongs to the more general area of the power to X technologies. Power to heat is, to our view, gaining a competitive advantage because of a number of reasons, which have been mostly mentioned in the previous lectures. Next slide. Thermal energy storage is going to play an increasing role. In our case, it was at the crossroad of two technologies. We have mentioned the role that thermal energy storage has played in allowing concentrated solar power. Today, thermal energy storage again plays a central role in power to heat. Our contribution has been that of showing the potential of fluidized bed technology in this field. I will shortly describe a very successful journey, which started some 30 years ago. I guess it was in 2010, probably, that we started thinking of new ways to store heat in a feasible, in a dependable way. And our school, our university, and our research centers were extremely qualified and competent in fluidization. Was mostly due to our mentor and Professor Leopoldo Massimilla, who was one of the pioneers, the founder and one of the initiators of chemical engineering in Naples. So it was quite easy for us to find that fluidization could have played a role in this context. And before you mention, I want to mention another person, and the other person is Gennaro De Michele. Gennaro De Michele was a former head of the research of Enel, one of the top managers, but with a very strong sensitivity to fundamental research. He came from our school, from the School of Naples, and together with us, he was one who inspired much the use of fluidization in this context. What is a fluidized bed? Fluidization is the process of making a powder to behave like a liquid. And this is accomplished by suspending the powder in an upflowing gas stream. We can find many occurrences of fluidization. Fluidization is a versatile technology which is widely used in industry, in energy, in chemical, pharmaceutical, and other industries. It may also happen that it occurs in nature. Among the topics that we have studied in Naples, there has been also the role of fluidization in pyroclastic flows, in generating the impact that volcanic eruptions of pyroclastic nature may impact. Fluidized beds have very peculiar features. This has been mentioned already by Fulvio before me. If you consider the key thermal properties, for instance, the effective thermal conductivity of a fluidized bed as a continuous medium, or an effective thermal diffusivity of a fluidized bed as a thermal medium, you will discover that they are on orders of magnitude, many orders of magnitude larger than most accumulation or storage media that have been considered in the past. If you compare the thermal diffusivity of a fluid bed, which may be in the range of 10 to the minus 2, 10 to the minus 3 square meters per second, and you compare this with the thermal diffusivity of graphite or of molten salts, you will realize that there are many, many orders of magnitude of difference, and the same takes place as you consider the thermal conductivity. And this takes place with a specific capacity, specific heat capacity, which is more or less the same. So when using a fluid bed, you can improve your system, you can improve your unit in terms of responsiveness and ability to get and give back heat without losing anything from the standpoint of storage capacity. This was the very simple, naive starting point of our development some 30 years ago. And then there are other, though, sorry, I just want to reinforce some other features. Fluid beds of sands are cheap, they are abundant, no supply risk. We have mentioned several times the significant risks on the supply chain for alternative ways to store energy, like critical raw materials supply. It may be operated over a broad temperature range, even beyond 1000 degrees C. This means that the heat that we are going to store will be high quality heat, which is amenable to get extremely good conversion to any other kind of energy. And a bed of sand, well, you can see some sand there. And a bed of sand presents no corrosion, pollution, and health hazard risks. So there are almost no drawbacks in using a bed of fluidized granular materials as an energy storage medium. Another advantage of fluidization is that it is extremely versatile. You can arrange a fluidized bed in different ways. There are many fluidization regimes, from dense bed to dilute beds to circulating beds. And you can tailor your fluid bed according to your prevailing desire, prevailing target. And our main activity has been that of moving away from the traditional applications of fluidized beds in combustion, in gasification, in calcination of ores, and to try to speculate what would have been the best operational condition and the fluidization regimes for the new purposes that the concentrated solar thermal and the power to heat challenges were opening up. The journey has gone through a sequence of milestones that I want to recall you. The first was the development of an indirectly heated concentrated solar fluid bed receiver. We had a proof of concept which was developed as early as in 2012. Eventually, we moved to a more challenging design of the concentrated solar thermal system, which was based on direct irradiation of the fluidized bed. First, a proof of concept and eventually a pilot scale, which has been operating in San Filippo del Mela in Sicily, as Fulvio mentioned before, for I guess a couple of years. The peak thermal power was 2 megawatts peak incident power. And that was a real challenge, and that was a real way to fully test the potential of fluid bed under very challenging conditions. And eventually, starting from that experience, we directed the attention to the application of a fluid bed to power to heat. And then there has been the pilot scale development, which you can see here in these premises, the MG test demonstration unit. What is going on now and what will be the future will be to try to move from thermal energy storage to thermochemical energy storage. When you have been able to capture energy in a fluid bed, there is a great potential to carry on endothermic, exothermic reactions in a fluid bed to take fully advantage of the thermicity of chemical reactions in storing energy. The journey has been documented by nearly 30 or the like very successful papers in the open literature. But what I want to underline was a very rewarding opportunity which links this presentation today to the SolarPACES conference. The picture to the lower left part was a special mention on the Magaldi STEM technology that was recognized at the closing ceremony of SolarPACES in 2016. That was in Abu Dhabi. And so SolarPACES was to some extent giving us a strong encouragement and a strong confirmation of the soundness and the potential of the intuitions. There has been a continuous and very rewarding, very successful interaction between the research institutes, the Department of Chemical Materials and Industrial Production Engineering of the University of Naples and the Institute for Science and Technology on Sustainable Energy and Mobility. All the solutions were tested at the lab scale, and then they were checked for their robustness, scaled up for application on the industrial scale application receiver. From concentrated solar power, we have gained all the relevant information to translate the technology to power to heat. And in particular, the very favorable properties of gas fluidized bed for thermal energy storage that had already been demonstrated in a much challenging environment that was the directly irradiated concentrated solar power unit of San Filippo del Melo provided a strong ground, a strong basement for the design of this unit. There are, of course, differences, there are peculiarities, but the robustness and the resilience of this device are strongly grounded and strongly rooted in the previous experience accumulated on the concentrated solar power unit. And with this, I would like to close my talk. And of course, we will be ready for any questions, any curiosities. I assume that may be many from all the participants to SolarPACES and any other. Thank you so much. Thank you, sir.